Welcome to Sleepy Science Student, where we explore the cosmos one peaceful breath at a time. Tonight, we're going on a slow, gentle journey to the red planet, Mars, a place that has captured human imagination for centuries, floating there in the night sky like a distant ember, calling to us softly across the void of space. I hope this video isn't too interesting, though, if it does happen to keep you awake, at least you'll be learning something fascinating about humanity's greatest adventure into the solar system. Not the worst way to spend a sleepless night, drifting through space in your mind while your body rests here on Earth. Before we begin our voyage to Mars together, I'd love it if you gave this video a like, and maybe even subscribed if you haven't already. It really helps this sleepy little channel grow and means more curious minds can find their way to these calm explorations of science and space. I'd also love to know where you're watching from and what time it is for you right now. Are you tuning in from a cozy bed in London at midnight, or listening from a hammock in Rio de Janeiro at sunset while the stars are just beginning to appear? Let me know in the comments. It's always such a joy to see our peaceful community scattered gently across the globe, all looking up at the same sky, wondering about the same distant worlds. Now, settle in. Get comfortable. You don't need to remember any of this. You don't need to take notes or stay alert. Just let the words wash over you, like soft Martian dust settling in the thin atmosphere. Let your shoulders relax. Let your breathing slow down. And as we begin this gentle voyage to Mars, remember, this video is for educational and relaxation purposes only. It's not intended as medical advice, astronaut training, or a guarantee that you'll actually make it to Mars in your lifetime, though dreaming about it is always encouraged. Ready? Let's begin. Let's talk about Mars, that curious red dot that has been watching us for as long as humans have been watching back. If you've ever looked up at the night sky and noticed a reddish star that doesn't quite twinkle like the others, you've probably spotted Mars. It's been there, quietly orbiting the sun since long before humans existed. Ancient civilizations noticed it too. The Egyptians called it Her, meaning the Red One. The Romans named it after their god of war, drawn to its blood-colored appearance. But Mars isn't angry or warlike. It's simply a cold, quiet desert world, patiently existing about 140 million miles away from us, give or take, depending on where both planets happen to be in their orbits. Mars has always occupied a special place in human consciousness. It's not too close. Like Venus, with its crushing atmosphere and hellish surface temperatures. It's not too far, like the gas giants Jupiter and Saturn, so distant they feel almost unreachable. Mars sits in what you might call the Goldilocks distance of human ambition, close enough to dream about, far enough to be challenging. It's a bit like that perfect hiking trail, difficult enough to feel like an achievement, but not so impossible that you give up before you start. The planet itself is about half the size of Earth. Imagine taking our world and shrinking it down, making it just a bit more modest, a bit quieter. Mars has roughly the same amount of land surface as Earth, though, because it has no oceans. All that reddish-brown terrain, stretching out in endless plains, massive canyons, and towering volcanoes. It's a world of extremes. The largest volcano in the solar system, Olympus Mons, rises there, so tall it would dwarf Mount Everest 3 times over. The deepest canyon system, Valles Marineris, stretches for thousands of miles, so vast you could fit the entire Grand Canyon inside it many times over, and still have room left. But what makes Mars truly remarkable isn't its size or its canyons, or even its massive volcanoes. It's the quiet possibility that whispers through every scientific observation we make. The possibility that Mars was once different. Warmer perhaps. Wetter. Definitely. A place where ancient rivers carved through rock and pooled into lakes, where rain might have fallen from clouds, where the conditions for life might have existed, however briefly, in those early days, billions of years ago. Why does this matter? Because Mars represents something profound in human nature. We are creatures who look at horizons and wonder what lies beyond them. Our ancestors crossed oceans on fragile boats, climbed mountains because they were there, ventured into unknown territories, armed with little more than curiosity and determination. Mars is simply the next horizon, the next mountain to climb, the next ocean to cross. Scientists have good, practical reasons for wanting to go to Mars. They want to study its geology, to understand how rocky planets form and evolve. They want to search for signs of past or present life, to answer one of humanity's oldest questions. Are we alone? They want to learn how to live on another world, testing technologies and techniques that might one day help us survive if Earth faces catastrophe. But beneath all these rational reasons lies something deeper, something harder to quantify in scientific papers and mission proposals. We want to go to Mars because we are human, and humans explore. It's woven into our DNA, this restless curiosity. We can't help ourselves. Show us a distant shore and we'll build a boat. Show us a red planet hanging in the night sky and we'll build a rocket. It's what we do. It's what we've always done. The decision to focus on Mars over other destinations wasn't random, though. Venus is closer, but utterly hostile, a hellscape of crushing pressure and heat that melts lead. Mercury is too close to the sun, baked and radiation scorched. The outer planets are gas giants without solid surfaces to stand on, and their moons, while fascinating, are so far away that the journey would take decades with current technology. Jupiter's moon Europa might have oceans under its icy crust. Saturn's moon, Titan, has lakes of liquid methane. These are wonderful, mysterious places, but they're patient. They can wait. Mars, on the other hand, is right there, relatively speaking, a neighbor in cosmic terms, and it offers something unique, a solid surface to walk on, a day that's roughly the same length as Earth's, seasons that change as the planet tilts on its axis, polar ice caps that grow and shrink with those seasons. It's different from Earth, certainly. The air is thin, mostly carbon dioxide. The temperature averages around minus 80 degrees Fahrenheit. There's no breathable oxygen, no liquid water on the surface, but it's not completely alien. There are familiar patterns there, familiar rhythms. It's strange enough to be fascinating, but similar enough to feel like we might actually belong there someday. Perhaps that's the real reason Mars calls to us. It feels achievable. Not easy. Nothing about going to Mars is easy, but possible. Within reach, if we just stretch a little further, if we just work a little harder, if we just dare a little more. And so, slowly, quietly, over decades of robotic missions and careful study, we've been preparing for the journey. Not just the physical journey across space, though that's certainly part of it, but the mental journey, too. The emotional journey, the collective decision that yes, we will do this. We will become a species that lives on more than one world. We will take that first gentle step onto Martian soil and plant a flag, not for any one nation, but for humanity itself. But what does that journey actually involve? How do you prepare to travel to another world? What challenges await in the cold darkness between here and there? Let's drift together into those questions, slowly, peacefully, as we explore what it really means to journey to Mars. Now, let's talk about distance. Not the kind you can measure with a ruler or drive in a car, but the vast, almost incomprehensible distance of space. Mars isn't always the same distance from Earth. Both planets orbit the sun at different speeds and along different paths, which means sometimes they're on opposite sides of the sun from each other, and sometimes they swing closer together. At their nearest approach, what astronomers call opposition, Mars can be about 35 million miles from Earth. At their farthest, when they're on opposite sides of the sun, that distance stretches to about 250 million miles. It's a bit like two runners on a track who sometimes lap each other and sometimes end up on opposite sides of the circuit. Let's pause for a moment and really consider what 35 million miles means. If you could drive a car at highway speed toward Mars, which you can't, obviously, but humor me for this gentle thought experiment, it would take you about 70 years of continuous driving to get there. No stops for gas, No sleep. Just you and the open cosmos and a very, very long road trip. That's how far away our close neighbor really is. This distance creates our first major challenge: timing. You can't just launch a rocket to Mars whenever you feel like it. The planets have to be in the right positions relative to each other. These favorable alignments happen roughly every 26 months, opening what mission planners call a launch window, a brief period, usually lasting a few weeks, when the geometry of orbits allows for an efficient journey. Miss your window, and you have to wait more than 2 years for the next one. It's a bit like trying to board a train that only stops at your station once every 2 years. You have to be ready. You have to be patient. You have to wait for your moment. During these launch windows, spacecraft take advantage of what's called a Hohmann transfer orbit, a curved path through space that uses the minimum amount of fuel to get from one planet to another. Think of it like this: you're not flying directly toward Mars. You're not aiming at where Mars is when you launch. Instead, you're aiming at where Mars will be months from now when you arrive. You're launching into a gentle arc that intersects with Mars's orbit at precisely the right moment. It's less like throwing a ball to someone and more like throwing a ball to where someone will be, trusting in gravity and mathematics to make the connection. This journey, under ideal conditions with current technology, takes between 6 and 9 months, half a year or more, floating through the void. Let that sink in for a moment. 6 to 9 months in a spacecraft, watching Earth shrink behind you and Mars grow slowly larger ahead. 6 to 9 months of recycled air and freeze-dried food, and the same few faces of your fellow crew members. 6 to 9 months of being farther from home than any human has ever been. But why does it take so long? After all, light from the sun reaches Mars in about 13 minutes. Why can't we just zoom there, at a fraction of that speed? The answer lies in the fundamental limitations of rocket propulsion and the tyranny of the rocket equation, a mathematical reality that every spacecraft designer grapples with. Here's the thing about rockets: most of their mass at launch is fuel. The more fuel you carry, the heavier your rocket is. The heavier your rocket is, the more fuel you need to lift that weight. The more fuel you need, the heavier your rocket becomes. It's a vicious cycle, a mathematical spiral that quickly reaches impractical extremes. To go faster, you'd need exponentially more fuel. To carry that fuel, you'd need bigger rockets. To launch those bigger rockets, you'd need even more fuel. Eventually, you hit a wall. There's only so much energy we can pack into chemical rockets, and we're already pretty close to that limit. So instead of brute force, just burning more fuel to go faster, mission designers use finesse. They use the gravity of other bodies to give spacecraft a boost. They carefully calculate trajectories that require the minimum energy. They accept that faster would be nice, but possible is better than impossible. And so, gently, patiently, our spacecraft drift toward Mars at speeds that feel agonizingly slow compared to science fiction, but are actually breathtakingly fast by any human standard, tens of thousands of miles per hour, slipping through the silence of space. During this journey, astronauts would experience something profound and strange. For the first few days after launch, they could look back and see Earth, that beautiful blue marble, growing smaller. They would watch their home planet, every person they've ever known, every place they've ever been, every tree and ocean and mountain, slowly shrink to a dot, then vanish into the blackness. Meanwhile, Mars would be invisible ahead of them, too small and distant to see clearly. For months, they would be suspended between worlds, belonging to neither, citizens of the void. This is why the journey to Mars is not just a technical challenge, but a psychological one. The isolation is profound. On the International Space Station, astronauts are only about 250 miles above Earth's surface. If something goes wrong, they can be home in hours. They can look out the window and see Earth filling their view, close enough to make out continents and clouds. They can have video calls with family with only a fraction of a second delay. They're still connected, still part of Earth's embrace. But on the way to Mars, everything changes. The farther you get from Earth, the longer it takes for signals to travel back and forth. At Mars distances, there's a delay of several minutes each way. You can't have a conversation. You can't call for help and get immediate advice. You send a message, then wait, and wait, and wait for the reply to crawl back across the void at the speed of light. If something goes wrong, if a system fails, if someone gets sick, if an emergency develops, the crew is entirely on their own. Mission Control can offer advice, but by the time that advice arrives, minutes will have passed. Precious minutes, maybe critical minutes. This is the fundamental loneliness of deep space travel. You are farther from help than any human has ever been. You are more alone than anyone in history, separated, not just by distance, but by time itself, by the delay that light and radio waves need to cross the darkness between worlds. It's humbling, it's terrifying, it's awe-inspiring, and yet, somehow, this journey calls to us. Maybe because we know our ancestors faced similar isolation when they sailed across oceans, not knowing what lay beyond the horizon. Maybe because we understand that all great adventures require courage, and all courage requires facing fear. Maybe because we simply can't help ourselves. We see Mars hanging there in the night sky, and we think, I want to go there. I want to stand on that distant shore. I want to be part of the story of humanity reaching beyond Earth. So we plan, we calculate, we build. We prepare for this long, slow journey through the darkness, knowing that at the end of it, if everything goes right, if all the systems work, if we've solved all the thousands of problems that need solving, we'll have accomplished something extraordinary. We'll have crossed the ocean of space and arrived at a new world, ready to take our first gentle steps on alien soil. But before we can take those steps, we need to survive the journey. And that brings us to the spacecraft itself, to the clever engineering and careful design that will carry humans safely across the void. Let's drift into that topic now, softly exploring the vehicles that will make this dream possible. Section 3. Now, let's talk about the spacecraft, the vessels that will carry human beings across the vast darkness between worlds. Designing a spacecraft for Mars is not like designing an airplane or even a space shuttle. Those vehicles operate relatively close to Earth, with the possibility of quick returns if something goes wrong. A Mars spacecraft needs to be entirely self-sufficient for months. A tiny bubble of Earth hurtling through the void, keeping its occupants alive in an environment that wants very much to kill them. The challenges are fascinating. First, there's the simple matter of propulsion. How do you push something heavy enough to sustain human life all the way to Mars? Chemical rockets, the kind we've used since the dawn of the space age, work through basic physics, burn fuel, expel hot gases out the back, and the rocket moves forward. It's Newton's third law in action. For every action, there's an equal and opposite reaction. Push something one way, and you move the other way. These engines are powerful, but they have limitations. Once you've burned your fuel, it's gone. You can't refuel in space. Whatever propellant you launch with is all you get. This is why the rocket equation is so tyrannical, why adding more fuel just makes you need more fuel to lift that fuel. It's an elegant problem, really. Frustrating, but elegant. Scientists and engineers have been exploring alternatives. Ion drives, for instance, use electricity to accelerate charged particles to incredibly high speeds. These tiny particles are expelled from the engine, providing thrust. The force is gentle. You could barely feel it pushing against your hand, but unlike chemical rockets that burn for minutes, ion drives can run for months or years, gradually building up tremendous velocity. It's a bit like the difference between sprinting and marathon running. Chemical rockets sprint. Ion drives run marathons. For cargo missions to Mars, where speed isn't critical and efficiency is everything, ion propulsion is elegant and practical. For human missions, though, you need something faster. 6 to 9 months is already a long time to spend in space. You don't want to stretch that journey even longer, so chemical rockets remain our primary option, at least for now. Big ones, powerful ones, rockets that can lift hundreds of tons off Earth's surface and send them speeding toward Mars. NASA's Space Launch System, designed for deep space missions, stands taller than the Statue of Liberty. When it launches, it produces more thrust than any rocket currently in operation. SpaceX's Starship, still in development, is even more ambitious. A fully reusable spacecraft designed to carry up to 100 people to Mars. Both systems represent decades of engineering refinement, countless tests, and the accumulated knowledge of every previous mission into space. But the rocket is just the first piece. Once you're in space, once the engines have shut down and you're coasting toward Mars, you need somewhere to live. The spacecraft that makes the journey, let's call it the transit vehicle, needs to be part spaceship, part hotel, part laboratory, and part refuge. It needs to protect its occupants from radiation, provide air and water and food, manage waste, maintain comfortable temperatures, and offer enough space that people don't go mad from claustrophobia after months in close quarters. Think about your home for a moment. You have rooms to move between. You can go outside. You can open windows. You have privacy when you want it. Now imagine living in a space about the size of a small RV with a handful of other people. For 6 to 9 months, you can never go outside. The walls don't change. The view doesn't change. Just blackness with distant stars. Everything you need must be brought with you or recycled from what you already have. It's an exercise in minimalism, in efficiency, in making do with just enough and nothing more. The life support systems are remarkable exercises in engineering elegance. Water, for instance, cannot be wasted. Every drop of humidity condensed from the air, every drop of sweat, every drop of urine, all of it must be captured, filtered, and purified for reuse. The water you drink today might be the same water you drank a month ago, recycled through sophisticated filtration systems until it's cleaner than most tap water on Earth. It sounds unpleasant, perhaps, but it's necessary. You can't carry enough water for a 6-month journey. You have to recycle. You have to close the loop. Oxygen presents a similar challenge. On Earth, plants constantly replenish our oxygen, turning carbon dioxide back into breathable air through photosynthesis. In space, you need technology to mimic that process. Systems that split water molecules into hydrogen and oxygen. Systems that absorb carbon dioxide exhaled by the crew and either store it or process it. It's not perfect. Some oxygen is inevitably lost, leaking slowly through seals and being absorbed by materials, but it's efficient enough that you only need to bring replacement oxygen, not the full supply for the entire journey. Food is more straightforward, but still challenging. Everything must be preserved, lightweight, and nutritious. Freeze-dried meals, similar to camping food, but more sophisticated. Vitamins and supplements to make up for the lack of fresh fruits and vegetables. Some missions might include small hydroponic gardens, growing fresh lettuce or herbs to supplement the diet and provide a psychological boost, something living and green in an environment that's otherwise mechanical and sterile. There's something deeply comforting about growing things, even in space, maybe especially in space. The spacecraft also needs power, lots of it. Solar panels work well near Earth, where sunlight is strong, but Mars is farther from the sun, receiving only about 40% of the solar energy that Earth gets. Solar panels are still viable, but they need to be larger, more efficient. Some mission designs include nuclear power sources, small, safe reactors that generate steady electricity for years without needing sunlight. Nuclear has become less scary as we understand it better. It's not bombs or meltdowns. It's controlled, steady power generation, quiet and reliable. Temperature control is another subtle challenge. In space, there's no air to carry heat away from your spacecraft. On the side facing the sun, temperatures can soar. In shadow, they plummet. You need radiators to dump excess heat and heaters to keep vital systems from freezing. It's a constant balancing act, managing the flow of thermal energy so everything stays within acceptable ranges. And then there's radiation. Oh, radiation. This deserves special attention, so we'll drift into it more deeply in a later section. For now, just know that space is flooded with radiation, from the sun, from distant cosmic sources, Earth's magnetic field protects us from most of it. On the International Space Station, you're still close enough to Earth to receive some protection, but on the way to Mars, you're exposed. The spacecraft needs shielding, thick walls, water tanks positioned strategically, materials chosen for their ability to block or absorb radiation. It's not perfect. Some radiation will get through, but you minimize the dose as much as possible, keeping your crew as safe as engineering allows. The design of these transit vehicles is a study in compromises. You want thick walls for radiation protection, but thick walls are heavy, and heavy means more fuel, which means more cost and complexity. You want lots of living space for psychological health, but space is volume, and volume is weight. You want backup systems for everything critical, but backups add mass and complexity. Every decision involves trade-offs. Every feature has a cost. The art is in finding the balance, the point where you have just enough of everything without carrying more than necessary. Some designs propose spinning the spacecraft to create artificial gravity through centrifugal force. Not real gravity, not the pull of a planet, but a similar effect. Spin in space, and you get pushed toward the outer wall. It feels like gravity, though it's really just inertia. This would be healthier for astronauts, preventing the bone loss and muscle atrophy that comes with prolonged weightlessness. But spinning adds engineering complexity. The spacecraft needs to be symmetrically balanced. Docking with a spinning vehicle is harder. Moving between sections becomes more complicated. So far, most designs stick with weightlessness and accept the health consequences, mitigating them with exercise and medication. Looking at these spacecraft designs, whether NASA's concepts, SpaceX's ambitions, or proposals from other space agencies around the world, you're struck by how much thought goes into every detail. The placement of sleeping quarters, the design of toilets that work in zero gravity, the psychology of color choices in interior spaces, the size and position of windows, or whether to have windows at all. Everything matters. Everything has been considered, tested, refined. These are not just machines. They're lifeboats. They're homes away from home. They're the thin shell of protection that stands between human life and the lethal void. And they need to work perfectly. Every system, every day, for months on end. The stakes are absolute. There's no pulling over to the side of the road if something breaks. There's no calling a tow truck. Whatever goes wrong, the crew must fix it themselves, or live with it, or die from it. This is why testing is so extensive, why every component is built with redundancy, why astronauts train for years to understand every system, every possible failure mode, every emergency procedure. Because when you're millions of miles from Earth, knowledge and preparation are the only things standing between life and death. But let's not dwell on the dangers too darkly. These spacecraft represent human ingenuity at its finest. They're the culmination of decades of experience, lessons learned from previous missions, innovations driven by necessity. They're proof that when humans want to go somewhere badly enough, we figure out how to get there. We solve the problems. We overcome the obstacles. We build the machines that make the impossible possible. And speaking of life support, of keeping humans alive in an unforgiving environment, let's drift now into one of the most critical aspects of the journey, the systems that provide air, water, and the necessities of life during those long months in the darkness between worlds. Section 4. Now, let's talk about the quiet systems that keep you alive, the ones you barely notice on Earth, but become absolutely critical in space. Take breathing, for instance. It's automatic. You don't think about it. Your body just does it, pulling in oxygen, expelling carbon dioxide, maintaining the delicate balance that keeps you conscious and alive. But in a sealed spacecraft, breathing becomes an engineering problem. Where does the oxygen come from? Where does the carbon dioxide go? How do you maintain the right mixture of gases in the air so it's not too rich in oxygen, which could cause fires, or too depleted, which would suffocate you? The International Space Station uses an elegantly simple system called electrolysis. Water, delivered from Earth or collected from the air as condensation, is split into hydrogen and oxygen using electricity. The oxygen is released into the air for breathing. The hydrogen is usually vented into space, though newer systems try to recombine it with carbon dioxide to create water again, closing the loop even more tightly. It's a quiet process, happening continuously in the background, maintaining the atmosphere without drama or fuss. Carbon dioxide removal is equally important. Too much CO2 in the air, and you'll get drowsy, confused, eventually unconscious. On submarines, they use chemical scrubbers, filters that chemically absorb carbon dioxide from the air. In space, similar systems work continuously, pulling CO2 out of the atmosphere and either storing it or combining it with hydrogen to regenerate water. Nothing is wasted if it can be recycled. Nothing is thrown away if it can be used again. For a Mars mission, these systems need to work for months without resupply. They need to be reliable, efficient, and redundant. If the primary oxygen generation system fails, there must be a backup. If that backup fails, there must be emergency oxygen supplies, tanks that can keep the crew alive long enough to fix the problem, or, in the worst case, long enough to say goodbye. Water is even more precious than oxygen. You can store compressed oxygen in tanks relatively easily. Water is heavier, bulkier, harder to store in large quantities, and yet, you need it constantly. For drinking, for food preparation, for hygiene, for generating oxygen, for cooling equipment. An adult human needs about 2 liters of water per day just for drinking. Add in washing, cooking, and other uses, and the requirement climbs higher. This is why water recycling is so sophisticated on spacecraft. The system used on the ISS recovers about 90% of all water on board, humidity condensed from the air. Every breath you exhale contains water vapor, and that vapor is captured. Sweat evaporating from your skin, captured. Urine, filtered, purified, made drinkable again. Even water used to wash vegetables or clean surfaces is recovered and recycled. It sounds unpalatable perhaps, but the filtration is so thorough that the recycled water is probably cleaner than most municipal tap water on Earth. Astronauts joke that today's coffee is tomorrow's coffee, which is technically true, but misses the elegance of the system. You're not drinking yesterday's urine, you're drinking water. Pure H2O molecules that happen to have been through your kidneys before, but are now as clean as any water anywhere. Water doesn't remember where it's been. It's just molecules. Chemistry doesn't care about history. For a Mars mission, bringing all the water you need would be impossible. The mass would be prohibitive, so you recycle with extreme efficiency, accepting that you might lose a small percentage to leaks or inefficiencies, bringing just enough extra to compensate. It's a careful calculation. Bring too much and you're wasting precious mass that could be used for other supplies. Bring too little and you risk running out. The margins are thin. The math must be exact. Food storage and preparation in space is its own strange art. Without gravity, liquids float, crumbs float. Opening a bag of chips would result in chips drifting everywhere, a slowly expanding cloud of snacks that you'd be chasing for hours. So space food is designed to minimize loose particles, bite-sized pieces, rehydratable meals, sticky sauces that cling to food and don't form floating droplets. It's practical, but it's also monotonous. The same textures, meal after meal. The same flavors from the limited menu. Fresh food is a luxury that lasts only days after launch. Then it's freeze-dried, vacuum-packed, and preserved. Some research has been done on growing fresh food in space. Small hydroponic gardens where lettuce or radishes grow under LED lights. Their roots in nutrient-rich water rather than soil. The yields are tiny, a few leaves of lettuce, perhaps a cherry tomato or two. But the psychological benefit is enormous. Something fresh, something growing, something green in an environment of metal and plastic. Astronauts report that these small gardens are profoundly important for morale. It's not really about the calories, it's about life, about growth, about having something living that's not just surviving, but thriving. On a Mars mission, food planning is a careful balance of nutrition, mass, variety, and psychology. You need enough calories, Activity in space burns energy, and you can't afford to lose too much weight. You need essential vitamins and minerals that fresh food normally provides, but preserved food lacks. You need enough variety that people don't develop food fatigue, where they'd rather skip a meal than eat the same rehydrated beef stroganoff for the 50th time. And you need comfort foods, little treats, familiar flavors that provide psychological comfort when homesickness sets in. Some of the meals are surprisingly good, according to astronauts who've tested them. Others are merely adequate. A few are, well, let's just say they're nutritious. The challenge is that in space, your sense of taste changes. Fluids shift in your body in weightlessness, causing nasal congestion similar to a cold. When you can't smell properly, food tastes bland. This is why space food tends to be heavily seasoned, spicy, with strong flavors that can punch through the dulled senses. Hot sauce is wildly popular. Bland food is left uneaten. There's also the matter of waste management, which is less discussed, but equally important. Everything you consume must be accounted for when it exits your body. Solid waste is typically dried, sealed, and stored, eventually to be jettisoned or returned to Earth for disposal. Urine, as we've discussed, is filtered and recycled. The toilets themselves are engineering marvels, using airflow instead of gravity to direct waste into the appropriate containers. They're not comfortable, exactly. They're functional. That's what matters. All of these systems, oxygen generation, carbon dioxide removal, water recycling, food storage, waste management, form what's called the Environmental Control and Life Support System, or ECLSS. It's a wonderfully bureaucratic acronym for something absolutely vital. The ECLSS is what keeps the interior of your spacecraft habitable. It's what stands between you and the vacuum outside. It runs constantly, quietly, in the background, maintaining the thin bubble of breathable air and drinkable water that keeps you alive. On Earth, nature provides all of this for free. The atmosphere is vast enough that your breathing doesn't significantly change its composition. Rain falls and rivers flow, and the water cycle continues without you having to think about it. You eat food grown in soil, enriched by decomposing plants and animals, part of vast ecological cycles that have run for billions of years. You don't notice these systems because they're everywhere, abundant, automatic. In space, you notice. Oh, how you notice. Every breath is a gift from the oxygen generator. Every sip of water is a small miracle of filtration and recycling. Every meal represents careful planning and precious mass budgeted in the mission design. You become aware, perhaps for the first time in your life, of how much you depend on the systems that support life, how fragile you are without them, how vulnerable. This awareness might be one of the most profound aspects of space travel. You learn, viscerally, that you are not separate from your environment. You need it. You depend on it, absolutely. Break the systems and you die. Simple as that. This understanding changes people. Astronauts who've spent time in space often return with a deeper appreciation for Earth, for the miracle of our atmosphere and water, and the abundant life that surrounds us. They've seen what it's like when those things aren't there, when you have to create them artificially with machines that can fail. And speaking of failure, speaking of things that can go wrong, let's drift now into one of the most insidious challenges of the Mars journey: radiation, the invisible threat that permeates space, that passes through walls and flesh, that poses risks we're only beginning to fully understand. Now we need to talk about radiation, though I'll try to make this as gentle as possible, because radiation is one of those topics that can sound frightening if we're not careful. Radiation is simply energy moving through space. Light is radiation, visible photons that let you see. Heat is radiation, infrared energy warming your skin. Radio waves are radiation, carrying music and voices through the air. Not all radiation is dangerous. In fact, most of it isn't. But some forms of radiation carry enough energy to damage living cells, and those forms are what we need to worry about in space. On Earth, you're protected from most of this harmful radiation by two invisible shields. The first is our atmosphere, a thick blanket of air that absorbs and scatters incoming radiation before it reaches the ground. The second is Earth's magnetic field, generated by the churning molten metal in our planet's core. This field extends far into space, creating a protective bubble that deflects charged particles streaming from the sun. Together, these shields are remarkably effective. You receive a tiny bit of background radiation on Earth, from natural sources like radon gas, from cosmic rays that manage to penetrate the atmosphere, from trace radioactive elements in rocks and soil. But the levels are low enough that your body's natural repair mechanisms handle any damage without problems. Leave Earth, though, and you lose these protections. The atmosphere thins and disappears. The magnetic field weakens and fades. Suddenly, you're exposed to the full flux of radiation flowing through space, and it's considerably more intense than what you experience on the ground. There are two main sources of radiation in space. The first is the sun. Our star constantly emits a stream of charged particles, mostly protons and electrons, called the solar wind. This stream is fairly steady and manageable, but occasionally the sun has what we poetically call a mood. Solar flares and coronal mass ejections that release bursts of high-energy particles into space. If one of these events happens to be aimed at your spacecraft, the radiation dose can spike dramatically. On the International Space Station, astronauts have designated shelter areas with extra shielding where they can wait out these solar storms. On the way to Mars, you need similar protected zones. The second source is more insidious: galactic cosmic rays. These are high-energy particles, atomic nuclei stripped of their electrons, that come from outside our solar system. Supernova explosions, billions of years ago in distant parts of the galaxy, accelerated these particles to incredible energies. They've been traveling through space ever since, and some of them happen to pass through our region of the galaxy. They're relatively rare. You're not being constantly bombarded by them, but they're energetic enough that when they do hit, they can cause real damage. The danger of radiation comes down to how it interacts with living tissue. When a high-energy particle passes through your body, it leaves a trail of damage in its wake. It can break DNA strands, damage proteins, kill cells outright. Your body has repair mechanisms. Evolution equipped us with remarkable molecular machinery that fixes most of this damage without problems. But if the radiation dose is high enough, or sustained over long enough periods, the repair systems can't keep up. Damaged cells might die, causing tissue to fail. Or worse, damaged cells might survive with mutated DNA, potentially leading to cancer years later. For short stays in space, weeks or months on the ISS, the radiation exposure is considered acceptable. Astronauts receive more radiation than the average person on Earth, but the increased cancer risk over their lifetimes is relatively small, balanced against the value of the scientific work they're doing. For a Mars mission, though, you're talking about 6 to 9 months in transit to Mars, months on the surface, then another 6 to 9 months coming home. The total radiation dose adds up to something more concerning. How much radiation are we talking about? It's measured in units called sieverts. On Earth, the average person receives about 3 millisieverts per year from natural background sources. Astronauts on the ISS receive about 150 millisieverts per year, 50 times higher than Earth's surface. On a Mars mission, without better shielding, astronauts might receive 1,000 millisieverts or more over the course of the journey. That's a significant dose, not immediately life-threatening, but enough to measurably increase the risk of cancer and other health problems later in life. So how do you protect against this invisible threat? The most obvious answer is shielding. Put something between you and the radiation. Thick walls, dense materials, lead, perhaps, or concrete. But here's where the problem gets interesting. Mass. Every kilogram of shielding is mass you have to launch from Earth, mass that requires more fuel, more cost, more complexity. You can't just wrap your spacecraft in meters of lead. It would be impossibly heavy. What you need is efficient shielding, materials that provide the best protection for the least mass. Water, surprisingly, is excellent. Hydrogen atoms in water molecules are light, but effective at absorbing and scattering radiation. Some spacecraft designs include water tanks positioned around crew quarters, serving double duty as both radiation shielding and water storage. Polyethylene, a common plastic rich in hydrogen, is also effective and lighter than metal. But even with clever shielding, you can't block everything. Galactic cosmic rays are so energetic that they pass through almost any reasonable thickness of material. What you can do is reduce the dose, bring it down to more manageable levels, and accept that some exposure is unavoidable. It's a risk assessment, a calculation of acceptable danger balanced against the value of the mission. Some mission designs propose waiting out solar storms in a small, heavily shielded shelter within the spacecraft, a storm cellar where the crew can huddle during periods of high solar activity. These events are somewhat predictable. We monitor the sun constantly, watching for flares and ejections, giving warnings hours or days before the particles arrive. It's not perfect. Space weather forecasting is still a developing science, but it helps. When the alert comes, you retreat to the shelter, wait for the storm to pass, then emerge when it's safe. On Mars itself, radiation is still a concern, but the planet offers some natural protection. Mars has a thin atmosphere, about 1% the pressure of Earth's, but even that thin layer blocks some radiation. More importantly, you can build habitats underground or pile Martian soil on top of surface structures. A few meters of regolith, Martian dirt, provides excellent shielding. Early Mars habitats might be partially buried, using the ground itself as protection. It's not elegant, living under dirt, but it's practical, effective, safe. There's also ongoing research into biological countermeasures. Can we develop drugs that help cells repair radiation damage more quickly? Can we boost the body's natural defense mechanisms? Can we identify people whose genetics make them naturally more resistant to radiation and select them for Mars missions? These are open questions, fascinating puzzles that researchers are working to solve. The radiation challenge doesn't mean Mars is impossible. It means Mars is hard. It means we need to be clever, creative, willing to accept some risk while minimizing it where we can. Astronauts understand this. They know the dangers. They accept them in exchange for the opportunity to be part of something historic, to push the boundaries of human experience, to go where no one has gone before. Perhaps the most profound aspect of the radiation challenge is how it illustrates the hostility of space. It's not actively trying to harm you. Space doesn't have intentions or desires, but it's deeply inhospitable to life. The conditions that make space beautiful, the vacuum, the cold, the vast distances, the flowing currents of charged particles, are the same conditions that make it lethal. We evolved for Earth, for thick air and warm sunlight and magnetic protection. Space is not our natural environment. Going there requires technology, planning, constant vigilance, and yet we go, or we plan to go, because the challenge is part of the appeal, because facing difficulty and overcoming it is deeply human, because radiation is scary but not insurmountable, dangerous but manageable, a problem that clever engineering and careful planning can address. Now, let's drift from the physical challenges, radiation and life support, and spacecraft design, to something more subtle but equally important, the psychological journey. The mental and emotional experience of being isolated for months in the darkness between worlds. Because the human mind is remarkable but also fragile, capable of incredible resilience but also vulnerable to the stress of extreme isolation. Now, gently, let's talk about something harder to quantify than radiation or rocket fuel. The human mind during long-duration spaceflight. Isolation is a quiet thing. It doesn't hit. It doesn't you all at once. It creeps in gradually, day by day, a slowly accumulating weight you don't fully notice until it's already pressing down on you. In the early days of a Mars mission, there's excitement, adventure, the thrill of leaving Earth and beginning this incredible journey. Astronauts are busy learning routines, adapting to weightlessness, marveling at the view of Earth receding behind them. There's too much to do, too much to experience, to feel lonely. But weeks pass, then months. The routines become tedious. The same faces, the same small space, the same recycled air. No fresh experiences, no new stimuli. Nothing changes except the slowly shifting positions of Earth and Mars outside your window. This is when isolation begins to bite, when the enormity of your separation from everything familiar starts to sink in. Humans are social creatures. We evolved in groups, tribes, communities. We need connection, variety, change. We need to see new faces, hear new voices, experience novelty. Deprive us of these things, and our mental health suffers. It's not weakness, it's biology. Our brains are wired to expect certain kinds of stimulation, certain patterns of social interaction. Take those away and the brain struggles, like a machine running without proper lubrication. The psychological challenges of a Mars mission fall into several categories. First, there's the monotony. Every day is essentially the same schedule, the same tasks, the same environment. On Earth, even if your daily routine is repetitive, there are small variations. The weather changes. You see different people. You drive past different scenery. In a spacecraft, there's no weather. There are no strangers. The scenery is blackness with stars, beautiful at first, but eventually just there, unchanging, eternal. Monotony breeds boredom, and boredom is corrosive. It makes time feel slower. It saps motivation. It makes small irritations feel larger than they are. You've probably experienced a tiny fraction of this during a long flight or a tedious meeting. That sense that time has stopped, that you're trapped in an eternal present with no escape. Now extend that feeling over months. That's what crew members face. Learning to cope with boredom, to find meaning and engagement despite the repetition, is a critical psychological skill. Then there's the social strain of living in very close quarters with a small group of people. On Earth, when someone annoys you, you can leave, go for a walk, visit a friend, get some space. In a spacecraft, there's nowhere to go. You're stuck with these same people, 24 hours a day, for the entire journey. Every quirk, every habit, every annoying trait gets magnified through constant exposure. Maybe someone chews loudly. On Earth, you'd notice it briefly, feel mildly irritated, then move on with your day. On a spacecraft, you hear it every single meal for months, and it starts to drive you slightly crazy. Or someone tells the same stories, repeatedly, or someone's routine disrupts your sleep, or there's a clash of personalities. One person is naturally messy, while another is obsessively neat. These small frictions compound over time. What starts as minor annoyance can escalate into real conflict, if not managed carefully. Space agencies understand this. Crew selection for long-duration missions includes extensive psychological screening. They're not just looking for technical competence. They want people who are emotionally stable, socially adaptable, good at conflict resolution, able to function well in teams. They run simulations, locking potential crew members in confined spaces together for weeks or months to see how they handle the stress. They train astronauts in communication skills, teaching them how to express frustrations constructively, how to listen empathetically, how to diffuse tension before it explodes. Even with careful selection and training, problems arise. The history of space stations includes stories of crew members who simply stopped talking to each other for weeks. Not out of malice, but from sheer exhaustion with each other's company. It's like the worst road trip you can imagine, except you can't pull over. You can't turn around and go home. You just have to endure until you reach your destination. Communication with Earth helps, but has its own challenges. As mentioned earlier, there's a signal delay that increases as you move farther from Earth, several minutes each way by the time you're near Mars. This makes real-time conversation impossible. You send a message, then wait for the reply. It's like the slowest text conversation ever, except you can include video. Family calls become asynchronous. You ask how your daughter's piano recital went, then wait 10 or 15 minutes for her answer to arrive. By then, you've moved on to other activities. The rhythm of conversation, the natural back and forth, is broken. There's also the simple pain of missing significant events: birthdays, holidays, weddings, the birth of a grandchild, your son's graduation. These moments happen without you. You can watch videos sent from Earth, but you're not there. You're millions of miles away, unable to participate, unable to hug, or hold, or be present. The guilt and sadness of missing these events weighs on astronauts. It's a sacrifice they make knowingly, but knowing doesn't make it easier. Some astronauts report experiencing something called the overview effect, a profound cognitive shift that comes from seeing Earth from space. The planet looks small, fragile, beautiful. All the boundaries that divide us, national borders, racial distinctions, ideological differences, become invisible. You see one world, one humanity, all of us floating together on this blue marble in the vastness of space. It's an awe-inspiring experience, often deeply emotional, that gives people a changed perspective on what matters in life. But there's potentially a darker side too. As Earth shrinks to a distant dot and eventually becomes indistinguishable from stars, some astronauts might experience existential dread, the overwhelming emptiness of space, the realization of how small and insignificant we are in cosmic terms, how fragile, how alone. Most people don't think about these things day to day. They're too busy living, too engaged with immediate concerns. But in the quiet of a spacecraft, drifting through the void, these thoughts can arise. They can be overwhelming if you're not prepared for them. Space agencies try to mitigate these psychological challenges in various ways. They maintain regular communication schedules, ensuring astronauts have frequent contact with family and mission control. They provide entertainment, books, movies, music, games. They schedule video calls with psychologists who can monitor mental health and provide support if needed. They design schedules that include variety, mixing up tasks and activities to combat monotony. They ensure adequate sleep, proper nutrition, and exercise, all of which help maintain mental health. Some missions include small comforts from home, favorite foods, photos of loved ones, personal items that carry meaning. Astronauts on the ISS report that these small connections to Earth are incredibly important. A picture of your spouse, your child's drawing, a lucky charm. These objects become anchors, reminders of what you're enduring this hardship for, what you have to return to when the mission is over. Exercise serves multiple purposes on long-duration missions. Physically, it's essential for combating muscle atrophy and bone loss and weightlessness. But psychologically, it's just as important. Exercise releases endorphins, improves mood, provides routine, gives you something concrete to accomplish each day. It's also a way to work off tension and frustration. Feeling angry, go run on the treadmill, or rather, be strapped to a treadmill so you don't float away while trying to run. Feeling anxious, spend time on the resistance equipment. The physical exertion helps calm the mind. There's also value in meaningful work. Astronauts on a Mars mission aren't just passengers. They're conducting experiments, maintaining systems, gathering data. Having important tasks to complete gives purpose to each day. You're not just surviving the journey, you're contributing to human knowledge, to the success of the mission. That sense of purpose is protective against despair. Looking at all these psychological challenges, you might wonder, is it worth it? Why put people through this stress? Why not just send robots, which don't get lonely or bored or miss their families? The answer is complex. Robots are amazing. We've learned an incredible amount about Mars from robotic missions. But humans bring something robots cannot: adaptability, intuition, the ability to make complex decisions quickly, hands-on problem solving. A rover encountering an unexpected obstacle might take hours to receive new instructions from Earth and execute them. A human can assess the situation instantly and find a solution. A robot can analyze rock samples. A human can appreciate the beauty of a Martian sunset and feel the profound significance of standing on another world. There's also something deeply human about wanting to go ourselves. We don't just want to know about Mars, we want to experience it, to stand on it, to look up at the sky and see Earth as a small blue dot and feel the weight of what that means. Robots can't feel that. They can't be changed by the experience. They can't come home and tell stories that inspire the next generation of explorers. So we plan missions that address the psychological challenges as best we can. We select resilient individuals. We provide support systems. We train crews in coping strategies. We accept that the journey will be hard, but believe it's possible. That humans can endure, can adapt, can make this journey and emerge intact on the other side. Changed perhaps, but whole. And speaking of arrival, let's drift now toward Mars itself, toward the complex and dangerous process of landing on another world. Because surviving the journey is only half the challenge. You also have to land safely, and landing on Mars is, to put it mildly, not easy. Now, gently, let's talk about one of the most nerve-wracking parts of the entire journey, landing on Mars. NASA engineers have a phrase for the landing process: 7 minutes of terror. That's how long it takes for a spacecraft entering Mars's atmosphere at hypersonic speeds to slow down and reach the surface. 7 minutes during which everything must work perfectly, because there's no room for error, no time for humans on Earth to help. The spacecraft is on its own, executing a pre-programmed sequence, and all mission control can do is wait for the signal confirming success or failure. Why is landing on Mars so difficult? The problem is Mars's atmosphere, specifically that it's not quite thick enough and not quite thin enough. Let me explain this peculiar difficulty. When spacecraft return to Earth from orbit, they use the atmosphere to slow down. Atmospheric drag creates heat, tremendous heat, enough to make the spacecraft's heat shield glow white hot, but it also bleeds away velocity. Parachutes can then finish the job, slowing the spacecraft enough that it can land safely. Earth's thick atmosphere is wonderfully useful for this purpose. Mars's atmosphere is much thinner, about 1% the pressure of Earth's at sea level. That's thick enough to create heat during entry. You definitely need a heat shield, but it's not thick enough to slow you down completely. Even with a large parachute deployed at the maximum safe speed, you're still falling way too fast when you reach the surface. You need something more. Some other way to shed that final bit of velocity. The moon has no atmosphere at all, which actually makes landing easier in some ways. You can use rockets for the entire descent, controlling your speed precisely all the way down. No heat shield needed, no parachutes. Just fire your engines at the right time and touch down, gently. Simple, relatively speaking. Mars sits in this awkward middle ground. Too much atmosphere to ignore, but too little to rely on completely. You need multiple systems working in sequence. Heat shield for initial entry, parachutes for mid-phase slowing, then rockets for the final descent. Each phase must work perfectly. Each transition must happen at precisely the right moment. And because of the signal delay between Mars and Earth, the 10 to 20 minutes it takes for radio signals to make the journey, the spacecraft must execute this entire sequence autonomously. It's been programmed, tested, simulated countless times, but ultimately, it's on its own during those 7 critical minutes. The entry phase begins when the spacecraft hits the top of Mars's atmosphere at about 12,000 miles per hour. At this speed, air molecules don't have time to move out of the way. They compress violently in front of the spacecraft, creating a shock wave and intense heat. The heat shield protects the spacecraft from temperatures reaching 2400 degrees Fahrenheit, hot enough to melt steel. The spacecraft doesn't slow down gradually during entry. It sheds velocity in a violent controlled crash through the thin air, experiencing deceleration forces several times stronger than Earth's gravity. Once the spacecraft has slowed to around 1,000 miles per hour, it deploys a parachute. This must happen at exactly the right speed. Too fast, and the parachute will tear apart. Too slow, and it won't provide enough drag. The parachute is enormous, designed to catch as much of Mars's thin air as possible. But even fully deployed, it can only slow the spacecraft to about 200 miles per hour, still far too fast for a safe landing. So the heat shield is jettisoned, explosively separated, and allowed to fall away, exposing the lander underneath. Radar begins measuring distance to the ground. The onboard computer calculates altitude and velocity, determining the exact moment to proceed to the next phase. That moment comes when the lander is still thousands of feet above the surface, traveling at 200 miles per hour. The parachute is cut away. Rockets ignite. And now begins the powered descent, the final, most critical phase, where engines must slow the lander from that terrifying speed down to zero in the last seconds before touchdown. Different missions have used different landing systems. The Mars Science Laboratory, which delivered the Curiosity rover, used an elaborate sky crane system, arguably one of the most audacious engineering solutions ever devised for a planetary landing. As the descent stage approached the surface on rocket power, it lowered the rover on cables, like a crane, then flew away and crashed deliberately once the rover was safely on the ground. It sounds absurd. It looks absurd in animations, but it worked, setting Curiosity gently on the Martian surface without raising dust that might contaminate the rover's instruments. For a human mission, the landing system needs to be larger, more robust, capable of delivering not just a rover, but a habitat, supplies, possibly multiple vehicles. The mass is much greater. The tolerances are tighter. Robots can survive rougher landings than humans. The landing site selection becomes more critical. You need relatively flat terrain, free of large rocks or steep slopes. You need to land precisely, within a few hundred meters of your target, so that multiple landers, carrying different components of your Mars base, end up close together. This precision landing requires sophisticated guidance systems. The spacecraft must identify landmarks during descent, compare them to onboard maps, and adjust its trajectory in real time. It's a bit like looking out the window of a descending airplane, recognizing which city you're approaching, and making small course corrections to hit the exact runway. Except you're doing this at hypersonic speeds with a computer, because humans can't react fast enough. Every Mars landing to date has been robotic. Everyone has involved mission controllers on Earth, watching nervously as telemetry streams in, delayed by those agonizing minutes, knowing that whatever is happening on Mars already happened. The spacecraft has either landed safely or crashed. They just don't know which yet. And every successful landing is celebrated with tearful relief, because they know how many things could have gone wrong, how many single points of failure existed in that 7-minute sequence. For a human mission, the stakes are immeasurably higher. It's not just equipment on the line, but lives. People inside that descending spacecraft, strapped in, waiting, feeling the deceleration forces, trusting in the systems, in the programming, in the countless tests that preceded this moment, unable to do anything but wait and hope. This is why so much emphasis is placed on reliability, on redundancy, on testing. You test the heat shield material in arc jet facilities that simulate entry heating. You test the parachutes in Earth's atmosphere at high altitude, approximating Mars conditions as closely as possible. You test the descent engines on test stands, firing them repeatedly to verify performance. You run computer simulations millions of times, trying different scenarios, different wind conditions, different atmospheric densities, making sure the guidance algorithms can handle variations. Even with all this preparation, landing on Mars involves risk, significant risk. Mars has a way of surprising us. Dust storms can change atmospheric density. Wind gusts can push a descending spacecraft off course. Hidden rocks can damage landing gear. There's always an element of uncertainty, of chance, that even the best engineering cannot completely eliminate. And yet, we plan to land humans there, because the alternative, abandoning the journey out of fear, feels wrong. Because humans have always faced dangerous frontiers and pushed forward anyway. Because the reward, if successful, is worth the risk. Imagine being inside that spacecraft during those 7 minutes. feeling the deceleration as you hit the atmosphere, the rattling and shaking as hypersonic winds buffet the heat shield, the sudden jolt when the parachute deploys, the brief moment of relative calm as you descend under canopy. Then the parachute drops away, and you're in free fall until the engines roar to life. The thunder of rockets, the final slowing, the computer counting down altitude, 100 meters, 50, 20, 10, 5, contact. The engines shut off. Silence. After months of engine noise and air circulation, sudden, profound silence. You're on Mars. You made it. You survived the journey through space and the violent descent through atmosphere. You're sitting on the surface of another planet, the first human to stand here, or part of the first group to stand here. Outside your window, through the settling dust raised by your engines, you can see the Martian landscape. Red-brown rocks, distant hills, a salmon-pink sky. This moment, this first glimpse of Mars from the surface, this realization that you've actually done it, will be one of the defining moments in human history. And it all depends on those 7 minutes of terror working perfectly. Every system, every phase, every calculated maneuver. Now, let's drift forward in our gentle exploration. Let's imagine that the landing was successful. The spacecraft is safely on the surface. The crew is alive, unbuckling their harnesses, preparing for the next enormous step, leaving the spacecraft and taking their first steps on Mars. Let's talk about what that moment might be like and what happens in those crucial early days on the surface of a new world. Now, slowly, let's imagine what it might feel like to step onto Mars for the first time. You're inside the landed spacecraft. The engines are silent. The vibration and noise of descent have faded. Outside your window is an alien landscape. Red-orange soil stretching to the horizon. Rocks scattered across the ground. Hills rising in the distance under a sky that's a peculiar shade of butterscotch pink. You know, intellectually, that you're on Mars. But it hasn't fully sunk in yet. Your mind is still catching up to what your senses are telling you. The first priority isn't stepping outside. It's making sure everything is working. You check all systems, life support, power, communications, structural integrity. You verify that the landing didn't damage anything critical. You establish contact with Earth, or rather, you send a signal toward Earth, knowing it will take 10 to 20 minutes to arrive, then another 10 to 20 for any response to come back. You follow procedures, methodically, even though part of you is screaming to just open the door and step out. But space travel is about discipline, about following protocols, about not letting excitement override caution. So you wait, you check, you verify. Only when you're certain everything is safe do you begin preparations to egress. Suiting up takes time. The Martian surface suit is not like the bulky spacesuits used for spacewalks in orbit. It needs to be more mobile, easier to work in, since you'll be wearing it for hours at a time. But it still needs to protect you from the environment. The thin atmosphere, the cold, the dust, the low pressure that would make your blood boil if you were exposed directly. So you seal yourself inside this protective layer, check all connections, verify your oxygen supply, test your communications. Then comes the moment. The airlock opens, the ramp extends, and for the first time in human history, a person stands at the threshold of another planet, about to take that first step. What do you say? Neil Armstrong's one small step line was planned in advance, a conscious piece of history making. The first person on Mars will face the same expectation. Something profound, something memorable, something that captures the significance of this moment. But what words can adequately express what it means to be the first human to touch alien soil? How do you summarize the centuries of dreaming, the decades of preparation, the months of journey, the terror of landing, all condensed into this single step? Maybe you keep it simple. Maybe you just say what you're feeling. We made it. Or maybe you think of everyone who made this possible, all the scientists and engineers and dreamers who contributed to this moment, and you say something about humanity rather than yourself. One world becomes two, perhaps. Or maybe in that moment, words fail completely. and you just step out, overwhelmed by the reality of where you are. The first sensation would be the gravity, or rather, the partial gravity. Mars has about 38% of Earth's gravitational pull. After months of weightlessness, even this partial gravity would feel significant. Your body would have weight again. Your muscles would need to work to hold you upright, but it would feel light, bouncy, almost. Each step would carry you further than on Earth. You could jump higher, move with a strange, dreamy quality, like walking underwater, but easier. The ground beneath your boots would be solid, rocky, covered in that fine red dust that's everywhere on Mars. The dust is actually iron oxide, rust essentially. Mars is red because its surface is rusty. The dust is fine, like talcum powder, and it gets into everything. It's also slightly toxic, perchlorate salts in the soil, so you can't let it contaminate your habitat or get into your life support systems. Managing the dust becomes one of the constant small challenges of living on Mars. Looking around, you'd notice the sky. On Earth, the sky is blue because of how our atmosphere scatters sunlight. Blue wavelengths get scattered, more than red. Mars's atmosphere is so thin and filled with suspended dust that the opposite happens. The sky appears reddish-pink during the day, fading to a blue-gray near the sun. It's backwards from what you're used to, visually disorienting, a constant reminder that you're not on Earth anymore. The sun itself looks smaller. Mars is farther from the sun than Earth, so the solar disk appears about 2/3 the size you're familiar with. The sunlight is dimmer too, about 40% of the intensity on Earth. It's not dark exactly, more like a perpetually overcast day. Everything has a subdued, muted quality to the light. Shadows are softer, colors are desaturated. It would take time to adjust to this new visual environment. Temperature is another immediate sensation. Even during the warmest part of a Martian day at the equator, temperatures might reach 70 degrees Fahrenheit at ground level, comfortable in a t-shirt if you were on Earth. But just a few feet above the ground, the air can be dozens of degrees colder, and once the sun sets, temperatures plummet, dropping to -100 Fahrenheit or lower. The thin atmosphere can't hold heat. It escapes rapidly into space once the sun goes down. Your suit would need excellent insulation and heating systems to keep you comfortable through these temperature swings. There's also an odd quality to sound on Mars. With such a thin atmosphere, sound waves travel differently. Everything would sound muffled, damped, quieter than on Earth. Your voice would have a strange quality to it. You wouldn't hear the wind the same way, even during dust storms. The thin air simply can't carry sound as effectively. It's a subtle thing, but it adds to the sense of alienness, of being somewhere fundamentally different. Those first minutes on the surface would be intensely busy. Photos to take, samples to collect, systems to check. You wouldn't just stand there marveling, though surely you'd steal moments to do that. You'd be working, executing the carefully planned first surface activities. But in the quiet spaces between tasks, the reality would wash over you in waves. You're on Mars, actually on Mars, standing on ground that no human has ever touched, looking at a landscape that has existed for billions of years in cold, patient silence, waiting for this moment when intelligent eyes would finally see it up close. The first surface mission would be short, maybe just an hour or two. You'd return to the safety of the lander, seal the airlock, remove your suit carefully to avoid bringing in dust. Then you'd have time to sit, to decompress, to let it all sink in. You did it. Humanity did it. After all the years of planning and preparation, after the dangerous journey and terrifying descent, here you are, on Mars. Over the following days, the routine would develop. Surface excursions lasting several hours, setting up equipment, solar panels, communication arrays, scientific instruments, practicing procedures for later, longer. Missions, getting comfortable with the environment, learning its rhythms and patterns. Each day, the sun rises in the east and sets in the west, just like Earth, though a Martian day, called a sol, is about 40 minutes longer than an Earth day. Your circadian rhythms would need to adjust, stretching slightly to accommodate Mars's rotation. And every day, You'd look at the sky and know that Earth is out there somewhere, a blue dot among the stars, impossibly far away. Your home, everyone you've ever known, everything familiar. It's all right there, unreachable, yet somehow present in your thoughts always. The homesickness would be profound, but so would the sense of achievement, the knowledge that you're part of something larger than yourself, that your presence here on this red, dusty world represents a milestone in human history. Let's drift now into what comes next. Not just visiting Mars, but actually living there, building habitats, establishing systems, creating the infrastructure that would allow humans not just to survive, but to thrive, turning Mars from a destination into a home. Now, gently, let's talk about what it means to actually live on Mars, not just visit. A short mission to Mars, landing, spending a few days on the surface, then returning to Earth would be an incredible achievement. But the real dream, the long-term vision, is to establish a permanent human presence, to build habitats where people can live and work for months or years, to create a self-sustaining outpost that doesn't depend entirely on supplies from Earth. This is harder than just landing, much harder, but it's also more meaningful, more transformative. It means humans becoming a multi-planetary species. The first habitat would likely be small and relatively simple, perhaps a prefabricated structure sent to Mars in advance of the crew, ready to be inflated and activated upon arrival, or maybe modules that need to be assembled, pieced together like an elaborate three-dimensional puzzle. Either way, the habitat needs to provide everything humans need: breathable air, drinkable water, comfortable temperature, protection from radiation, space to move around, places to sleep and work and exercise. Early habitat designs often look like large barrels or cylinders, with rounded shapes that handle internal pressure well. Sharp corners and flat walls want to bulge outward when you pressurize them. Curves distribute the stress more evenly. Inside, you'd have living quarters, a laboratory, a galley for food preparation, a bathroom, storage areas, an airlock for entering and exiting. Everything compact but functional. Think of it like an extremely well-designed tiny house, where every square foot serves multiple purposes, and storage is built into every available space. Protection from radiation remains critical. On Earth, we don't think about radiation much, because the atmosphere and magnetic field handle it for us. On Mars, with its thin atmosphere and absent global magnetic field, surface radiation is higher than Earth, but lower than deep space. Still, for long-term habitation, you want shielding. The elegant solution is to build underground or to pile Martian soil, regolith, on top of surface structures. A few feet of dirt provides excellent protection. It's not glamorous. It means living in what's essentially a bunker. But it's safe, effective. And the regolith is right there, free for the taking. Some habitat designs propose 3D printing structures, using Martian regolith itself as the building material. Mix it with binders, feed it into a printing system, and slowly build up walls and domes layer by layer. This would reduce the amount of construction materials you need to bring from Earth. Use local resources wherever possible. This principle, called in situ resource utilization, or ISRU, is fundamental to making Mars settlement practical. The less you have to ship from Earth, the cheaper and more feasible the endeavor becomes. Water is the most critical resource. Mars doesn't have liquid water on its surface. The pressure is too low, the temperature too cold. But water exists on Mars as ice. The polar caps are water ice mixed with carbon dioxide ice. The subsurface in many regions contains water ice, sometimes just a few feet below the surface. Some areas show evidence of buried glaciers, massive deposits of ice covered by dust and rock. If you can access this ice, melt it, and purify it, you have a local water supply. This is transformative. Water for drinking, water for making oxygen, water for growing plants, water for cooling equipment, water for making fuel. Everything becomes easier if you have a reliable local water source. Extracting subsurface ice isn't trivial. You need to dig or drill, then heat the ice to melt it, then collect and purify the resulting water. This requires energy, lots of it. Solar panels work on Mars, but are less efficient than on Earth because of the dimmer sunlight and the dust that accumulates on them, reducing their output. You need to regularly clean the panels, which is tedious but necessary. Nuclear power generators offer an alternative: steady, reliable power, regardless of dust storms or nighttime. Small reactors designed for space use generate electricity for years without needing refueling. The technology is proven and safe, though it carries psychological and political baggage because nuclear sounds scary to many people. Growing food on Mars is one of the most appealing challenges. Bringing all your food from Earth is possible, but expensive and limiting. If you can grow even some of your food locally, it reduces the supply chain burden and provides fresh nutrition. Plus, there's enormous psychological value in having living plants around. Green things growing. Life in a lifeless world. It's hope made visible. Martian soil is chemically suitable for plant growth. It contains the necessary minerals and elements, but it's missing organic material and beneficial microbes that Earth soil has. It also contains those toxic perchlorate salts we mentioned earlier, so you can't just scoop up Martian dirt and plant seeds. You need to wash the soil to remove perchlorates, then enrich it with organic matter and bacteria. Or you can grow plants hydroponically, roots suspended in nutrient-rich water with no soil at all. Either way, you need light, which means either transparent domes allowing in sunlight or artificial LED lighting tuned to the wavelengths plants need for photosynthesis. Early Martian greenhouses would be small, producing lettuce, radishes, cherry tomatoes, crops that grow quickly and provide fresh vitamins. Potatoes are a frequently mentioned candidate because they're calorie-dense and relatively easy to grow. The movie The Martian popularized this idea, showing an astronaut surviving on Mars-grown potatoes. While that scenario was fiction and overly simplified, the core concept is sound. Potatoes, with their high yield per square foot, are a practical crop for space agriculture. Over time, as the settlement grows, you could expand agricultural capacity, multiple greenhouse modules, more sophisticated systems. Perhaps even genetically engineered crops optimized for Martian conditions. Plants that grow in low light, tolerate cold better, resist radiation. This is speculative, but plausible. If we're terraforming our crops, making them more Martian compatible, we're taking the first steps toward transforming Mars itself. But let's not get ahead of ourselves. In the early days, the settlement would be tiny. A handful of people living in cramped conditions, entirely dependent on complex life support systems, working constantly to maintain the habitat and conduct research. It would be difficult, stressful, isolating, and yet also extraordinary. You'd be pioneers, living on another planet, proving it can be done, paving the way for those who come after. Daily life would involve a mix of scientific research, habitat maintenance, resource extraction, and agricultural work. Everyone would need to be multi-skilled. You can't afford pure specialists when your population is 5 or 10 people. Everyone needs to understand the life support systems. Everyone needs to be able to repair equipment. Everyone contributes to growing food, managing waste, keeping the habitat running. There would be routines, of course. Routines help maintain sanity. You wake at a set time, exercise to combat the health effects of partial gravity, eat breakfast together as a crew, important for maintaining social cohesion, then split up for the day's work. Science experiments, surface excursions, system checks, growing food, fixing whatever broke overnight, lunch, more work, maybe a video call with Earth, accepting the delay, dinner, some downtime, watching movies, reading, hobbies, then sleep, and the cycle repeats. But within that routine, there would be moments of profound wonder. Watching the sun set over Olympus Mons, the largest volcano in the solar system. Observing one of Mars's 2 small moons, Phobos or Deimos, Racing across the night sky, they orbit so close and fast that Phobos rises in the west and sets in the east, backwards from Earth's moon. Seeing a dust devil spiral across the plain, a whirling column of dust dancing in the thin air. Finding a rock with unusual texture or color and wondering about its history, the forces that shaped it over billions of years. These moments remind you why you're there, not just to survive, but to explore, to discover, to expand human knowledge and presence beyond Earth. Every day on Mars is a day further into humanity's future. Every problem solved is a lesson for those who come after. Every successful crop harvest, every system upgrade, every scientific discovery adds to the body of knowledge that will make the next mission easier, safer, more successful, and slowly, gradually, the settlement would grow. More crew arriving on subsequent missions, more habitats assembled, more greenhouses, more power generation, more resources extracted from Mars itself. What starts as a tiny outpost, a fragile toehold on an alien world, could become something larger, a research station, a town, eventually, perhaps, a self-sustaining colony that doesn't need Earth's support to survive. But we're getting ahead of ourselves again. That's a distant future. For now, let's stay focused on the early challenges, the first steps, the immediate difficulties of making Mars habitable. One of those challenges we haven't fully addressed yet is Martian weather. Let's drift into that topic now, exploring the atmospheric phenomena that early settlers would need to understand and adapt to. Now, softly, let's talk about Martian weather, the atmospheric patterns and phenomena that would shape daily life on the red planet. Mars has weather. That might surprise you if you think of Mars as a dead world, but it's quite dynamic. There's a thin atmosphere, yes, but it moves. It flows. It creates patterns. Clouds form and dissipate. Frost appears and sublimates. Dust storms arise and travel across the surface. The planet has seasons as its tilted axis causes different hemispheres to receive more or less sunlight throughout the Martian year, which lasts about 687 Earth days. The winds on Mars are curious things. The thin atmosphere means that even fast-moving air doesn't carry much force. A wind of 60 miles per hour on Mars has roughly the same force as a 6-mile-per-hour breeze on Earth. So contrary to science fiction portrayals, you wouldn't be knocked over by Martian winds. You wouldn't feel violent buffeting. The wind would be gentle, almost imperceptible against your suit. But what the wind lacks in force, it makes up for in its ability to move dust. Martian dust is incredibly fine, particles smaller than those in cigarette smoke. This dust remains suspended in the atmosphere easily, and wind can lift it from the surface, creating dust devils, those whirling columns of dust we mentioned earlier. These are common on Mars, more so than on Earth. Small ones happen almost constantly in some regions. They're beautiful in a strange way, like small tornadoes made of rust-colored mist, dancing across the landscape. But dust on Mars can also create larger-scale phenomena. Regional dust storms are common, covering hundreds of miles, lasting for days or weeks. These are inconvenient. They reduce visibility, coat everything in dust, decrease solar panel efficiency, but they're manageable. You stay inside, wait them out, clean your equipment afterward. Then there are the global dust storms. These are rare, happening roughly once every 3 Martian years, but they're spectacular. A storm starts in one region, grows, merges with other storms, and eventually envelops the entire planet in a thick haze of suspended dust. The sky turns opaque. Sunlight dims to a murky gloom. Temperatures change. The dust absorbs sunlight, warming the upper atmosphere while shadowing the surface. These global storms can last for months before finally settling. For solar-powered equipment, a global dust storm is a serious problem. Sunlight reaching the surface can drop to just 1% of normal levels. Rovers and habitats relying on solar power must either have massive battery reserves or switch to alternative power sources. This is another reason nuclear power is attractive for Mars settlements. It works regardless of what the atmosphere is doing. During a global storm, outdoor activities would be severely limited. Visibility drops to near zero. You could get lost just meters from your habitat. Navigation systems would still work, but the environment becomes hostile in new ways. The storm itself isn't dangerous. Remember, the wind force is low, but the reduced visibility and solar power create risks. Early settlers would need to plan for these events, ensuring they have sufficient stored power and supplies to last through months of darkened skies. There's something almost meditative about imagining a global dust storm from inside a Mars habitat. You're sealed inside, protected, listening to the soft whisper of dust particles against the walls. Outside, the world has disappeared into an orange haze. You can't see the hills, the rocks, the horizon. Just diffuse, murky light filtering through the dust. It's like being inside a snow globe someone shook violently, except instead of snow, it's rust-colored dust, and instead of settling quickly, it stays suspended for weeks. You have no choice but to wait, to trust your systems, to occupy yourself with indoor tasks and hope your power reserves hold out. But Mars weather isn't all about dust. There's also frost. Water ice frost forms on the surface at night in some regions, creating a thin, sparkling layer that sublimates, turns directly from ice to vapor when the sun rises and temperatures increase. Carbon dioxide frost also forms, especially at the polar caps. Mars is cold enough that CO2, a gas at Earth temperatures, freezes solid. The polar caps are made partly of water ice and partly of dry ice, frozen carbon dioxide. As seasons change, these caps grow and shrink dramatically. A significant fraction of Mars's thin atmosphere literally freezes out at the poles during winter, then sublimates back into gas during summer. The atmospheric pressure fluctuates with the seasons because of this. Clouds do exist on Mars, though they're thin and wispy compared to Earth's fluffy cumulus clouds. They're made of water ice crystals, forming at high altitude where temperatures are coldest. During summer in some regions, you might see early morning clouds that disappear as the day warms. There are also clouds of carbon dioxide ice at very high altitudes and during winter. Watching these delicate ice clouds drift across the pink sky would be hypnotizing, familiar enough to remind you of Earth, strange enough to reinforce that you're somewhere alien. Rain never falls on Mars, at least not in the present epoch. The pressure is too low for liquid water to exist. Any water vapor that condenses goes directly to ice, and that ice sublimates back to vapor. But billions of years ago, when Mars had a thicker atmosphere, it may have rained. Ancient river valleys, carved into the surface, suggest flowing water, possibly from rainfall, possibly from melting ice, possibly from groundwater seeping out. These ancient waterways are fossils now, dry channels hinting at a wetter past when Mars might have been more Earth-like. The daily temperature swings on Mars are dramatic and would take getting used to. Unlike Earth, where the ocean and thick atmosphere moderate temperature changes, Mars's thin air can't store much heat. During the day, especially in equatorial regions during summer, ground-level temperatures might reach comfortable levels. But just a few feet up, it's much colder, and as soon as the sun sets, everything plummets. The temperature can drop 100 degrees Fahrenheit or more between afternoon and night. Your habitat would need excellent insulation and active heating to maintain comfortable conditions through these swings. Thermal management becomes a constant engineering challenge, dumping excess heat during the day, conserving heat at night. The Martian year, being longer than Earth's, means each season lasts longer. An Earth year has 4 seasons of roughly 3 months each. A Martian year has 4 seasons of roughly 5 to 6 months each. Spring on Mars is a slow, gradual warming. Summer stretches longer than you're accustomed to on Earth. Autumn is a protracted cooling. Winter is an extended deep freeze. The long seasons would affect everything: planting and harvest cycles in greenhouses, power generation from solar panels, dust storm frequency, even psychological mood. Seasonal affective disorder might be more pronounced when winter lasts half a year. Understanding these weathers Patterns would be crucial for early settlers. You'd watch weather reports from orbital satellites, tracking dust storms, monitoring temperature trends, planning surface activities around conditions. You'd learn the rhythms of Martian weather, just as farmers on Earth learn their local climate. You'd know which seasons are best for certain activities, which regions are safest for habitats, when to expect storms, and when to expect clear skies. And in the quiet moments, during those clear days, when the dust has settled and the sky is its clearest salmon pink, you might look up and see Earth, a bright point of light in the Martian sky, appearing near sunrise or sunset depending on orbital positions. For Mars, Earth, and Moon look like a double star, 2 points of light close together. Seeing your home planet reduced to a dot, knowing everyone and everything you knew before this journey is there on that tiny point of light, it would be humbling, perspective shifting, a reminder of both how far you've come and how much you left behind. Now let's drift into a deeper question. What does Mars teach us about ourselves, about human nature, about our place in the cosmos? Because going to Mars isn't just a technical challenge or a scientific endeavor. It's also a philosophical and spiritual journey, one that changes how we think about humanity's future and our relationship with the universe. Let's explore what Mars means beyond the engineering and science, the deeper lessons embedded in this journey to another world. Going to Mars forces us to ask fundamental questions about who we are and what we're doing here. Why do we explore? What drives this urge to venture beyond the familiar? Is it just curiosity or something deeper? Is it wisdom to expand beyond Earth, or hubris to think we can survive elsewhere? There's an argument that we should fix Earth's problems before reaching for other worlds. Why spend billions on Mars when there's poverty, disease, environmental destruction here? It's a fair question, but it presents a false choice. We don't have to choose between Earth and space. We can address problems here while also pushing outward. Human capacity isn't finite in that way. The technologies developed for Mars, life support, recycling, renewable energy, efficient agriculture, often have applications back on Earth. The perspectives gained from space, the overview effect we mentioned earlier, make people more aware of Earth's fragility and value. Mars also offers a form of insurance. Earth is vulnerable. Not imminently, not dramatically, but genuinely vulnerable. An asteroid impact, though unlikely in any given century, is inevitable over long enough timescales. Climate change, whether natural or human-caused, poses risks to civilization. Nuclear war remains a possibility. Pandemics can spread globally in weeks. By establishing human presence on multiple worlds, we reduce the existential risk to our species. If something catastrophic happens to Earth, humanity continues elsewhere. It's not giving up on Earth. It's loving Earth enough to preserve what it has created: human consciousness, culture, knowledge, even if Earth itself faces disaster. But beyond insurance, Mars represents something psychological and spiritual. Humans need frontiers. We need challenges that test our limits. We need goals that require cooperation, ingenuity, and determination. For much of human history, exploration of Earth provided this. There were always new lands beyond the horizon, new mountains to climb, new oceans to cross. Now Earth is fully mapped. There are no blank spaces on the globe anymore. Some people feel constrained by this, like we're running out of room to grow. Mars provides a new frontier, not to escape Earth, but to expand the sphere of human experience. The journey to Mars also teaches practical lessons about survival. On Earth, we take for granted the systems that support us: atmosphere, water cycle, food webs, climate stability. We live within these systems without understanding them deeply. On Mars, you have to recreate these systems artificially. Every breath requires technology. Every drink involves recycling. Every meal represents careful resource management. This teaches appreciation for Earth's natural systems and reveals how they work. The lessons learned from surviving on Mars might help us survive better on Earth, making our civilization more sustainable, more resilient, more aware of the cycles and systems that support life. There's also something profound about standing on Mars and looking at Earth in the sky. The philosopher's stone of perspective. You see Earth not as the world, not as the center of everything, but as a world, one planet among many, unique and precious certainly, but part of a larger cosmos. This shift in perspective might be one of the most valuable outcomes of Mars exploration. It could change how we think about nationalism, tribalism, the artificial divisions we create. When you see Earth as a small, fragile sphere hanging in the darkness, political borders seem absurd, national conflicts seem petty. You realize we're all on this one lifeboat together, drifting through an immense and mostly empty universe. Mars also raises questions about life itself. If we find evidence that Mars once had life, microbial life, simple organisms in ancient water, it would suggest that life arises readily when conditions are right. That would mean the universe is probably full of life, at least simple life, on countless worlds, orbiting countless stars. We wouldn't be alone, even if we're the only intelligent species in our corner of the galaxy. If we don't find evidence of past life on Mars, that's interesting too. Mars had liquid water. It had the chemical ingredients. It had energy from sunlight and geothermal sources. If life didn't arise there despite favorable conditions, maybe life is rarer than we think. Maybe Earth is more special, more unusual. Maybe the emergence of life requires not just the right conditions, but also luck, a chance series of chemical reactions that might happen on one world in a billion. Either answer, life is common or life is rare, profoundly affects how we see ourselves. If life is common, we're part of a living universe, and intelligence might be common too, meaning we might one day encounter other civilizations. If life is rare, Earth's biosphere might be one of the few oases in a mostly sterile cosmos, making our existence all the more precious and remarkable. Living on Mars also changes the concept of home. For the first Mars settlers, Earth would still be home, the place they came from, the place they remember. But for their children, if any are born on Mars, what is home? Is it the planet they were born on but have never seen clearly through the dust? Or is it Earth, the world in the sky their parents tell stories about? These second-generation Martians would be truly multi-planetary humans, bridging two worlds, belonging fully to neither. This raises questions about identity. What does it mean to be human when some humans live on Earth and others on Mars? Do we remain a single species, a single culture, or do we diverge, developing different traditions, different values shaped by different environments? Living on Mars would be so different from living on Earth that Martian culture would inevitably evolve in unique directions. Practical adaptations, dealing with partial gravity, living in confined spaces, managing scarce resources would shape how people think and behave. After generations, Martians might feel more connection to their fellow Martians than to Earth-dwelling humans. Not hostile, perhaps, but separate, different. There are also ethical considerations about how we treat Mars. Should we preserve it as a pristine wilderness, studying it without altering it? Or is it ethical to terraform Mars, to change its atmosphere and climate deliberately, making it more Earth-like? Terraforming is speculative. We're not sure it's even possible, but the idea is to release greenhouse gases, warm the planet, thicken the atmosphere, perhaps even create oceans again. If we could do this over centuries or millennia, Mars might become a second Earth, a place where humans could eventually live without spacesuits. But would this be right? Mars has existed in its current state for billions of years. Do we have the moral authority to reshape an entire planet? Some argue that Mars is lifeless, so we're not harming anything. It's just rock and dust. Others say that Mars has intrinsic value beyond any life it might harbor, that its current state is worth preserving, that changing it would be an act of cosmic vandalism. These questions don't have easy answers. They require us to think beyond immediate practical concerns to deeper philosophical issues about our relationship with nature, with the cosmos, with the future. Going to Mars forces these conversations. It makes us confront what we value and why. In the quieter moments on Mars, watching the sunset and the stars emerge, astronauts might experience something transcendent, a sense of connection to the cosmos, the realization that they're standing on a world that's been here for 4 billion years, witness to countless sunrises and sunsets, patient and cold and ancient, now finally hosting intelligent observers who can appreciate its stark beauty. There's a privilege in that, a responsibility to do it right, to honor the planet by learning from it, to respect what it is while exploring what it could become. Mars doesn't change humanity's fundamental nature. We'd still be competitive, cooperative, curious, flawed, brilliant, contradictory creatures. But it provides a context for expressing those qualities in new ways. It offers challenges that require our best efforts. It promises discoveries that expand our understanding. It presents a future where human potential unfolds across multiple worlds instead of being confined to one. And perhaps that's the deepest lesson Mars teaches, that we're not finished yet. Humanity's story is still being written. Earth was our cradle, the place where we evolved and grew up, but we don't have to stay in the cradle forever. There are other worlds waiting, silent and patient, ready to receive us if we dare to make the journey. Mars is the first beyond Earth that feels truly reachable. Going there proves we can leave our birth world and establish ourselves elsewhere. After Mars, what next? The moons of Jupiter, the asteroid belt, eventually, perhaps, other star systems. The journey begins with Mars, but it doesn't end there. Let's drift now to our final section before the closing, a look forward to what a mature Mars settlement might look like, and what it might mean for humanity's long-term future among the stars. Section 12. Now, peacefully, let's imagine what Mars might become. Not in the early desperate days of survival, but decades or centuries later, when Mars has truly become humanity's second home. Picture this slowly. A colony that started with 6 people has grown to hundreds, then thousands. Multiple settlements dot different regions of Mars, some near the equator for warmer temperatures, some at mid-latitudes near water ice deposits, some in ancient lava tubes that provide natural radiation protection. These settlements are connected by a transportation network. Rovers travel between them on established routes. Communication relays ensure constant contact. Mars has become not just an outpost, but a society. The habitats have evolved from those early cramped modules into something more expansive. Multi-level structures, some above ground, but shielded with regolith. Others excavated into cliffsides or built in natural caves. Skylights and light tubes bring in Martian sunlight, filtered and distributed throughout living spaces. The interiors are no longer purely functional. They have art, plants, colors, comfortable furniture. People have stopped merely surviving and started living. The economy has diversified. Scientific research continues. Mars is an incredible laboratory for geology, astronomy, climate science, and astrobiology. But there's also mining. Mars contains valuable resources: water ice, metals, rare earth elements. Some materials are processed and used locally. Others might eventually be exported to orbital facilities where they are worth more than on Earth because they didn't have to be lifted out of Earth's deep gravity well. Manufacturing has begun. 3D printing, using Martian materials, producing construction components, tools, equipment. Agriculture has become sophisticated. Multiple greenhouse complexes produce diverse crops. Genetic engineering has created plant varieties optimized for Martian conditions. Species that grow well in low light, tolerate higher radiation, thrive in local soil. The diet is no longer freeze-dried rations, supplemented with occasional fresh lettuce. It's varied, nutritious, sometimes even delicious. Someone has figured out how to brew beer using Martian-grown ingredients. Someone else makes decent bread in the lower pressure. These small luxuries matter psychologically. They make Mars feel like a real place, not just a scientific expedition. Children have been born on Mars. This is profound and complicated. Pregnancy in lower gravity raises medical questions we haven't fully answered. How does fetal development proceed in 38% gravity? Are there complications? Do babies born on Mars develop differently? These first Martian children are experiments in a sense, not deliberately, but inevitably. They're healthy so far, in this imagined future, though their bodies are adapting to Martian conditions in ways that might make visiting Earth difficult later in life. They've never felt full Earth gravity. Would they even be strong enough to stand on Earth? Or would 1G feel like crushing weight after growing up in 0.38 G? These children grow up with a fundamentally different perspective than their parents. To them, Mars isn't alien, it's home. The salmon pink sky is normal. The red dust is just dust. Earth is the alien world, the blue one in the stories their parents tell. They dream of visiting Earth someday, seeing oceans and rain and forests, but they're not sure they'd want to stay. Mars is where they belong. This generational shift marks the moment when Mars transitions from a human outpost to a human home. When people are born there, live their lives there, and might die there without ever leaving, Mars has truly become a second branch of human civilization. The culture that develops on Mars would be distinctive. Practical necessities shape values. Self-reliance is paramount. You can't depend on Earth to rescue you. Cooperation is essential. Everyone's survival depends on systems working, which requires everyone contributing. Resourcefulness is celebrated, finding creative solutions with limited materials. Environmental awareness is deep. Martians understand intimately how life support works because their lives depend on it daily. These values might create a society that's different from Earth's in subtle but important ways. Religion and spirituality would evolve too. Some people brought their Earth faiths to Mars and maintained them, finding space for their beliefs in this new context. Others developed new spiritual perspectives influenced by the Martian environment. There might be something like Martian Buddhism, a philosophy emphasizing simplicity, interdependence, acceptance of harsh conditions, or Martian humanism, celebrating human ingenuity, valuing the community above the individual, finding meaning in pushing boundaries. These aren't replacements for Earth religions, but additions, new branches growing from old roots, shaped by the unique challenges and perspectives of living on another world. Education on Mars would emphasize practical skills alongside traditional academics. Every child learns basic life support, maintenance, agriculture, mechanical repair, first aid. You can't afford specialists who can't help in an emergency, but there's also focus on arts, humanities, history, maintaining connection to human culture broadly, not just the technical necessities of survival. Music, painting, storytelling, philosophy, these things matter. They're what make life worth living, what separates surviving from thriving. A Mars settlement that loses its humanities becomes mechanistic, sterile, sad. Culture is part of what you're preserving and extending across the solar system. Governance presents interesting challenges. Early settlements would likely be run by space agencies or corporations that funded them. But as populations grow and settle permanently, questions of self-governance arise. Do Martians have representation in Earth governments, or do they govern themselves? What laws apply on Mars? Can you really enforce Earth laws on a planet hundreds of millions of miles away? What happens when interests diverge between Earth and Mars? Science fiction has explored these themes, the inevitable independence movement, Mars breaking free from Earth's control, possibly even conflict between worlds. Real life might be less dramatic. Perhaps Mars gradually gains autonomy through practical necessity rather than revolution. Perhaps Earth and Mars remain partners, recognizing that cooperation benefits both. Or perhaps humanity develops new models of governance suitable for multi-planetary civilization, forms we haven't imagined yet because we've never needed them before. Trade between Earth and Mars would be limited by the sheer distance and time involved. Shipping physical goods takes months and costs tremendous amounts of energy. What makes sense to trade are things with high value and low mass: information, intellectual property, specialized manufactured goods, perhaps genetic material or pharmaceuticals. Raw materials like water or iron have no value for trade, too heavy, too common. But unique Martian organisms, if discovered, or materials with unusual properties found nowhere on Earth, or scientific data from Mars-based observations, these might be valuable enough to justify the expense of transport. Tourism is often mentioned as a potential Martian industry, rich adventurers paying enormous sums to experience Mars firsthand. This might happen eventually, but it raises questions about how to manage tourism without disrupting the serious work of settlement. Do you create tourist facilities separate from working settlements? Do you require extensive training to ensure tourists don't endanger themselves or others? How do you handle the psychological challenge of tourists who thought they wanted the Mars experience but can't handle the reality? These are solvable problems, but they need careful thought. Looking further ahead, centuries into this imagined future, Mars might have cities, real cities with populations in the millions, not spread across the surface. The surface remains hostile, but concentrated in regions with the best resources and conditions. Perhaps mostly underground, in vast excavated complexes that extend kilometers below the surface, or in massive pressurized domes several kilometers across, enclosing enough volume for buildings, parks, even weather. The technology for such structures doesn't exist yet, but in a future where Mars has industrial capacity, where resources are abundant and engineering sophisticated, such things become plausible. These cities would still look nothing like Earth cities. The architecture would be constrained by the need for pressure containment, radiation shielding, efficient use of space. But within those constraints, there would be beauty. Martian aesthetics reflecting the red planet's colors, rust reds, dusty browns, the salmon pink of the sky, public spaces where people gather, transportation systems moving people between districts, markets, schools, hospitals, entertainment venues, the full complexity of human society transplanted to and adapted for an alien world. And beyond Mars, what then? The asteroid belt, rich in resources, might be next. The moons of Jupiter, Europa with its subsurface ocean, Ganymede and Callisto with their ice, Saturn's Titan with its thick atmosphere and hydrocarbon lakes. These are harder destinations than Mars, more distant, more extreme, but they're possibilities. A civilization that has established itself on Mars has proven it can live away from Earth. After that, it's just a matter of scaling up ambition and capability. Some thinkers imagine a future where billions of humans live in rotating habitats throughout the solar system. O'Neill cylinders and Stanford Torrey, enormous structures built from asteroid material, providing Earth-like gravity through rotation. Not planets, but artificial worlds with controlled environments, vast interior spaces open to the sky. These megastructures are speculative, far beyond current capability, but not impossible, just difficult, just requiring resources and engineering on a scale we haven't attempted yet. Others imagine generation ships, vessels that travel for centuries toward other stars, carrying populations large enough to maintain genetic diversity and cultural continuity. The travelers who depart wouldn't live to see the destination. Their great-great-great-grandchildren would arrive, founding humanity's first settlements beyond our solar system. This is even more speculative, requiring technology we don't have, and resources almost unimaginable. But it represents the ultimate extension of the journey that begins with Mars, spreading humanity outward, making us a truly spacefaring species. These visions of the far future might seem like fantasies. Perhaps they are. Perhaps we never get beyond a few small Mars settlements. Perhaps the challenges prove too great, the costs too high, the political will insufficient. That's possible, but it's also possible that we surprise ourselves, that we discover we're more capable, more determined, more adaptable than we realized, that the first steps to Mars inspire the next generation to take further steps, and the generation after that goes further still. Progress isn't inevitable, but it's possible. The choice is ours. And now, gently, let's bring this long journey to a close. Let's return to where we started, full circle, but changed by everything we've explored together. Let's close our eyes to Mars and drift back into the comfortable quiet of Earth, bringing with us the wonder and possibility we've discovered. What is the journey to Mars? It's the question that brought us here, whispered softly at the beginning, like a child asking if we're brave enough to leave home. And after wandering through spacecraft designs, radiation challenges, isolation's weight, surface landings, habitat construction, weather patterns, philosophical questions, and distant futures, we find ourselves gently circling back to where we began, still wondering. We've learned that Mars isn't just a destination. It's a mirror that reflects humanity's dreams and limitations back at us. We've explored how the red planet sits in that perfect middle distance, not too close, not too far, calling to us with the promise of being difficult but achievable. We've discovered that the journey involves not just crossing physical distance, but psychological distances too, enduring isolation and monotony while maintaining hope and purpose. Maybe the point isn't whether we reach Mars in 5 years or 50. Maybe it doesn't matter whether settlements grow large or remain small. Maybe the whole meaning lies in the reaching itself, in the decision that we will try, that we will push beyond the familiar, that we refuse to be confined forever to the one world where we were born. The universe doesn't need us to explore it, but we need to explore, because exploration is woven into what makes us human. Mars is simply the next beautiful, terrible, wonderful challenge we've set for ourselves. So, with all of this in mind, are you still awake? If you are, I hope it's not because I was too interesting. Though, if I was, well, at least you've learned a few things about humanity's next great adventure along the way. And if you're already halfway to dreamland, may your thoughts be filled with rust-colored horizons, butterscotch skies, and the quiet satisfaction of imagining yourself standing on distant soil beneath alien stars. Before you drift off completely, I'd love to know where you're listening from and what time it is in your part of the world. Drop a comment and share. Are you perhaps someone who dreams of being among those first Mars explorers, or someone who finds comfort in imagining worlds you'll never visit? Are you an aspiring astronaut, or just someone who enjoys falling asleep to soft voices describing impossible places? If you found this gentle journey to Mars relaxing or informative, or both, please do consider giving this video a like and subscribing to Sleepy Science Student. It's a small gesture that helps me keep bringing you more calming, curious content from the world of science, space, and beyond. Each subscription reminds me that there's a community out there, scattered across this pale blue dot, looking up at the night sky and wondering what might be possible if we just dare to try. Thank you for joining me on this journey toward Mars. Sleep well, dream deep, and may your slumber be as peaceful as the ancient red deserts waiting quietly for humanity's first footsteps. Remember, we are made of star stuff, as Carl Sagan said, and the stars are calling us home to explore the cosmos that created us. Good night.